Welcome back to the classroom. My name is Mr. Wong, and today we're going to be looking at Module 8 from the universe to the atom, inquiry question 2 with a focus of Millikan's all droplet experiment. Okay, so what we're going to try and do is investigate the process to calculate the charge on an electron. We're going to look at some derivations of formulas. You can, if you like, try and work out the numerical answer, but there's quite a few, so I'm going to focus on just the derivations. I'm going to try and describe Millikan's all-drop experiment and what was that why was that influential in terms of the charge or to the structure of the atom. Okay, before we start, let's have a look at a couple multiple choice questions. So what did the invention of the cathode rays, why was that important? And also the second question is why was there a problem for scientists in deciding if cathode rays were particles or waves? What was the main factor that was making it difficult at the time? If you want, now's a good time to start pausing the button and answering, because I'm going to go through the answers now. So in question A, the invention that helped us to understand cathode rays led to the discovery of electrons, because electrons are cathode rays. B, what was the problem scientists had in deciding if cathode rays were particles? The answer was, were they charged? If you recall, in the previous video, we were saying the reason why they couldn't determine if it was negatively charged or positive charge at the time was because the vacuum tube didn't have a low enough air pressure. Okay, so because of that, or the vacuum wasn't sealed enough to a really small percentage of air. We do know it is negatively charged, so that's no longer an issue, but that was one of the things they thought at the time. We also looked at Thompson's experiment. So this wasn't the exact simulation I used, but thank you for the creator, Mr. Crook, for making this simulation that I used for many years. And we actually worked out the charge to mass ratio of the electron. So if you recall, let's just go over the formula. Charge to mass ratio of an electron. The formula we used was this one here, BR squared. So that's what we did. We also talked about how he changed the electrode. So what he tried to do was he changed the cathode here and the anode here, and he still saw these beams of cathode rays, or now that we know electrons coming through. So he decided that these electrons must be subatomic. So electrons are subatomic. They are smaller than the atom. And the actual design is these negative charges are embedded in a sea of positive charges around this positive sphere. We do know that's not the exact structure. We will go through it later on. So that's what we have here. Okay, so onwards. Alright, so the person we're going to highlight today is a guy called Millikan. Now, Millikan had a very important contribution to the electron. As you would know from the end of last lesson, J.J. Thomson only provided the charge to the mass ratio. He didn't actually provide the actual charge of the electron. Millikan's experiment actually helps us work out one important factor is the charge of an electron is quantized, so it's a fixed number, and he gave us a really close value to the one that we have today. Okay, so just a little conclusion or summary of what Thomson found. He found that the charge to mass ratio was this value here. He found that these particles were 1 in 2,000th smaller than the mass of a hydrogen atom. And he found that these subatomic particles can be found in all types of atoms of elements. Named them electrons, and don't forget he won a Nobel Prize for this. Okay, so let's try and deconstruct Millikan's oil drop experiment. So he has a thing called the atomizer. Well, actually, let's start from the front. So a closed chamber, as you can see here, and at the bottom he had two charged plates, one positive, one negative. The atomizer sprays a fine mist of droplets, so you see the droplets coming out here, and gravity is pulling it down. So if we try and show the thing, so gravity, force of gravity is pushing these particles down, these oil droplets. In that positioning, the space between the plates is ionized, causing electrons from the air to attach itself to the oil droplets. So in this particular spot here, this little thing here, because of the charged plates, it causes any electrons in the air to attach itself onto the oil droplets. A very intuitive way to measure the charge of the electron. This will make the oil droplets negative, and then obviously depending on the force, if the force of gravity was bigger than the force of the electric field, the electrons or the oil droplets would go down. If it was the opposite, if the force of the gravitational field is smaller than the electric field, it will go up. If we can somehow manage to make it go into equilibrium where it's similar to each other, we can make it sort of levitate in the middle. And there's some really interesting applications we can do, is the fact that we can measure the volume, the mass, and then using those two calculations, work out the charge of these oil droplets. Okay, so again, this is just another way of showing the actual structure. We have the oil droplets, atomizer, we have the X-ray source ionizing radiation. Okay, so there's that, and then we have the charged droplets. So that's what we have there. Okay, so if we actually have a look, there's a nice little simulation that we can use. Again, the links to this simulation will be in the links below. Let's just quickly have a look. Okay, so let's use a little squeezer here. We're going to press it, and you see the oil droplets either go up, being attracted by the positive plate, or they go down, they're being pulled by gravity here. Now, if I have a look at this, we know that the voltage that's being applied into this particular plate is 16.1 volts. And this particular oil droplet here, it's in equilibrium, meaning by the force of the electric field is equal to the force of the gravitational field. And so we have here, there's a couple of calculations that we can do to actually work out the charge of the electron. Firstly, we know the density of oil, that value there. If we calculate volume, we can work out the mass of the droplet, and then we can also, from there, find the force of the electric field equate to the gravitational field to then work out the charge of the oil droplet. Okay, so let's use some numbers I found earlier here. Now I know that the formula for volume is this value here, and we know that mass is equal to density times volume. Okay, so I'll just show you a quick calculation of what we have. Just go back. So I know that the radius, if I read through carefully, is around about, in this case, 590 nanometers. So if I substitute it in this formula here, just move it up here, make sure to convert into meters. we get a volume of approximately, and I'll just do it to 3 sig figs, just because I'll run out of space, 19 meters cubed. That's the volume. If I then substitute the volume into this equation down here, I'll know the mass of my oil droplet, or for this specific oil droplet. So 900 is the density times the volume. So in my calculations, I actually use the entire value, not the approximate value that I wrote up there. And I find that the mass of this oil droplet, again, to 3 sig figs, just for simplicity's sake, is 7.74 times 10 to the power of minus 16 kilograms. So that's the mass of the oil droplet. Okay, I'm going to go and divert to a couple of multiple choice questions, and then we'll look at how can we use these numbers to work out the charge of that oil droplet. Okay, so question A, this is actually taken from the additional sample paper. You can always look at that to test your understandings. I might put the link to that one as well, just for convenience for everyone. So the question we have here is, which of the following is true in relation to Millikan's oil droplet experiment? So what was the aim of that particular experiment? Was it to find the charge to mass ratio, measure the charge to mass ratio, charge of electron? Well, obviously C and D are the options we're looking at. He only looked at the charge of electrons. Thomson looked at the charge to mass ratio of electrons, and not Millikan. So what did he use? Did he use electric fields and magnetic fields, or did he just use electric fields only? Okay, answer is pretty straightforward here. It's D, electric fields only. Now, according to NESA, this is equivalent to 2 to 3 in terms of band. So it's really just recalling information. So if you can recall basic information of the experiment of different scientists, that's, in their eyes, a band 2 or a 3 range. Next one, this is also taken from the sample paper. So in an experiment, an electrically charged oil drop was suspended in air by an electric field. The electric field could be adjusted to balance the weight of the oil drop, so try and suspend it in the middle. If more drops were suspended and measurements taken, which of the following properties would all the oil drops be observed to have in common? Is it A, the same mass of each drop would be a multiple of the fundamental mass? The mass of each drop would be the same as each of the other drops? C, the charge of each drop would be a multiple of the fundamental charge? Or D, the charge of each drop would be the same as each of the other drops? So I'll let you pause it here if you want. We'll go through the answers and what the implication of this is in 1, 2, 3. So the answer is C. Okay, so if I increase the amount of droplets, and we'll show that in a second, if I increase the amount of droplets, yes, it does increase the mass, but we know that there is no fundamental mass of the oil that we're looking at here. Can't see that. Charge, however, we can calculate different values of charges, but what we will see is each charge has a common factor in it. So if we have a common factor, if we have a common number from each of these multiples, that means there has to be a fundamental number for charge. Any other numbers we get is a multiple of that charge. Okay, so you can use this to help you summarize, make some summary notes of how the experiment works. I'll switch over to the answers. Okay, and I'll move on. You could use this simulation as well. I'll leave it in the links as well. Okay, so let's actually look at the mathematics involved here. So if we have an oil droplet that's suspended between two charged plates, okay, remember this oil droplet is negatively charged due to the electrons are latching onto it. We know that the force of gravity, or the gravitational force, is mg, and the force exerted on a charged particle by the electric field is this. Now notice this is assuming that we have a uniform gravitational field and we have a uniform electric field here. Okay, so I could simply rearrange this. If I know the strength of my electric field and the gravitational field, I can simply rearrange this formula over like so, and that would give me a value for the charge of the electron. If I didn't know the charge of the electric field and I need to work out if I only knew the voltage and the distance between the two plates, so this particular distance here, then I can rearrange it this way. And let's see what we get here. This is not correct, so I'll just readjust that. So we have 1 over E, just move that out of our equation. Now we know that the strength of the electric field is V over D. So if I have the inverse of that, D is on top, V is at the bottom here. Okay, so I moved E across, well actually that's still correct because I just moved it across. So we have mgd over V. So I can use this equation to find out the charge of the electron, or I could use this equation to find out the charge of the electron, depending on what variables you know of. Now in the actual experiment, Millikan actually already calculated multiple masses of the oil droplets, and he found multiple values of charge. But there was one very distinct factor that was seen. The main idea was most of the droplets he found, the charges came in integers or intervals of the same common number. So what he found was the fundamental charge, the smallest charge that he could find, was this value here, 1 minus 1.5, because that's negative charge, 9, 10 to the power minus 19 coulombs. Okay, so what he was able to find was he would find the double of that particular charge, triple of that particular charge, or even more. But it still came back to this charge as the common factor. So what he predicted was those numbers that he found, he might have found the charge quantity of 2 electrons. He might have found a different one, a charge of 1 electron or 3 electrons, like so. Obviously this is a little generalized, but nonetheless, not only did he find the charge of 1 electron particle, he also found that it was quantized, so it is a fixed number. Okay, so you can have intervals of this number if you're looking at multiple electrons, but you cannot have a fraction in between. Charge can't be quantized, basically saying. Or not quantized, so it has to be quantized. Okay, so that's what we have here. So that was his discovery, the charge value and the fact that charge is quantized. Now you might notice that this number is not quite the same as the one we now know today, and obviously there was a little bit of error that's still involved, but that was the first time we actually realized that charge was indeed quantized, and the approximate value of the charge of the electron. Okay, so just some concluding information. We know that it was actually 6% error of the accepted value. So in current day standards, the number is still a little quite inaccurate, but it was close to, if you had to be real nitpicky, not too bad. But as we can see, most of the values are just multiples of this value at the time there. So the end conclusion gave us the value of the charge on an electron, and any other thing we see in terms of the charges. All charges were simply more charges of the same magnitude. So 3.2 would be 2 times the charge, 4.8, 3 times the charge of what he originally had, or what we now know today. Okay, so a couple of questions for you to attempt. So draw a diagram to show the forces acting on the oil droplet. Okay, so we know what that is. The oil droplet was being forced down by the electric field, and it was being, or gravitational field, sorry, and it was being forced up by the electric field, force of the electric field. Okay, the reason it has to be in this manner, because obviously we know that gravity always pulls an object towards the surface. In this case, we're looking downwards, so the force of the electric field has to pull our oil droplet upwards. Calculate the electric field strength between the plates. So electric field strength is V over D. Okay, so we have our value here, we have our potential difference here. So it's just 1,800 over 2.5. Make sure to convert that into meters, and that'll give you your value. In this experiment, which plate would be the positively charged? So our force is pulling our electric field up, which also implies that our electric field is going upwards. Okay, so what that means, or actually easier way of figuring out, the force is going upwards. Almost tricked myself there. So that means the electron is going up. Now, electric fields, opposite charges attract. So if the electron is going up, that means the top plate is positive, bottom plate is negative. Would the charge on the droplet be positive or negative? Okay, so really depends on what we're looking at here. The electric plates are that. This potential holds a charge drop between them. So in this case, because it's going to the positive plate, that would mean we have a negative charge. If the charge on the oil droplet was equal to 15 electronic charges, calculate the mass of the drop. Okay, so that one we are looking at equating this equation that we found earlier. So we have the charge value, 15 times that, and then rearrange. Okay, so consistent with what we said just then, positive, negative, and as you can see, 15 times the charge of the electron rearranged to give us a mass of that. So that's the approximate mass if we add 15 electronic charges, or 15 electrons basically. Alright, what I would like you to do, there's 2 past paper questions that you can look at. One is, again, from the additional sample paper, module 15. There's the actual guidelines. It's worth 6 marks, so it's a decent sized question. And the actual band range, if you have a look, is from band 2 to band 6. So obviously you can assume where those bands are given on the spectrum here. It says analyze this experiment to assess the effectiveness. Now remember, analyze, pros, cons, assess, judgment. Okay. And the last one, this is one designed by yours truly. With reference to the experimental evidence gathered by cathode ray tubes, describe the nature of these cathode rays. So, what is the actual properties of cathode rays. That's another thing you can look into. And that's pretty much ends our summary topic, or takes us to our summary stage. Goes through everything we learned today about Millikan's oil drop experiment. Remember, the main takeaway from it is he found the value of 1.59. It's not as accurate as we know today, but it did show that the charge of an electron is quantized. That's kind of the really important takeaway there. Okay? It's not continuous, it's quantized. And with that, thank you for joining this lesson. I'll see you again next time when we talk about Geiger and Marsden's experiment with the gold foil experiment and the proton.